Hello, everybody. So this is Psych 3280, week 8, neural-based subconsciousness. And this week, I'm going to talk about consciousness and attention. So before starting this week's, I wanted to first go over the main points of week 1 to 7, because this is supposed to be after the midterm recess. So I wanted to refresh main parts for you. So first, the overall structure of this class is to learn the basics of the neuroscience of consciousness. Especially week 1 to 7 was focused on the basic aspects of the neuroscience of consciousness, and that is composed of 3 parts. One is phenomenology. I asked a couple of times for you to introspect your experience, and first starting with a natural scene viewing. What do you see when the completely unexpected stimulus is presented on the display? What kind of stuff you see? So this is the first step. And then I also asked you to introspect what you see in terms of the color at the periphery, and how does it actually get affected by eye movements, with or without eye movements, through several demos. And I also introduced a couple of demonstrations through the website showing backward masking and binocular rivalry or motion-induced blindness, and then also visual after effects of motion and color, including after images. And then I also focused on some of the case reports from brain lesion patients. That's a very important kind of starting point for understanding phenomenology when some parts of the brains are damaged. And then the second part of the basic of the neuroscience of consciousness is about data, and the most important being the anatomical connections between the brains, at the large scale, or between neurons. And I also discussed about the anatomical structure of the eyes, especially in relation to peripheral color experience. And then the basic biophysics of the neurons, mainly dendrites collects input from other neurons, and then axons sends a pulse of action potential or spiking, firing to other neurons. And then I also mentioned about several different types of the behaviors, mainly button press, but also verbal reports types data, and some of them can contain non-conscious processing. And then also it's related to anatomy and the neurons, but the important concepts of receptive fields and the columnar organization in the visual cortex. Receptive fields are going to be important for this week's topic. And then again, another important topics for this week is the visual hierarchy and different kind of pathways in the visual system. And then I focus mainly our visual areas, V1 to V4, and MT, visual motion area, IT, inferotemporal cortex, and 2 higher areas, FFA and PPA, fusiform face area and the parahippocampal place areas. And then I haven't actually emphasized much on the theory bit, and this is going to be a bit of the main focus from week 8 to week 12, the advanced part of this class. And but I mentioned and reviewed the neural correlates of consciousness as a sort of a theoretical guide to do the empirical research of the consciousness experiment. And then I mentioned also Crick and Cox V1 hypothesis, whether V1 is out from the conscious experience, is discussed a couple of weeks ago. And then related to theory, but it's distinct from theory of consciousness, I also introduced a couple of methods. One was the signal detection theory that is important to both quantify the objective accuracy of the tasks and also subjective metacognitive accuracy, how much you know what you're doing in relation to blind side patients, betting behavior, wagering behaviors, type 1, type 2 signal detection theory. And then also I briefly reviewed various measures of the neurons, neuronal measures, functional MR, magnetic resonance imaging, fMRI, electro or magnetoencephalography, brain waves, and then electrical corticogram, that's the direct recording from the surface of the brain inside the skull. And then I also talked about single neuron recording and the microstimulation of the brain areas last week in human patients. That's very important for consciousness research. In particular, so that's sort of the overview over the last 7 weeks. So you have roughly now the basics of neuroscience of consciousness to consider more advanced topics. And then the last week, in particular, we talked about the neural correlates of the color qualia, which is likely to be located in B4 or B8. And then also neural correlates of the perception of objects, especially in IT and within objects, particularly faces in FFA. And then we talked about the patient who cannot see the object like VAS, but can see the faces. That was a YouTube video and showing that that kind of dissociation demonstrates that faces are highly likely to be a very special kind of objects in the world, and generates this feeling of faces in distinctive manner. And then I also talked about neural recording from human patients, epilepsy patients who are awake and they can talk about our Aston experience, and then especially focused on the human hippocampus. And then towards the end, I also introduced the phenomenology of the binocular rivalry when the two inputs to the left eye and the right eye are discordant. The experience changes between them, and then I introduced this finger type rivalry or this whole type rivalry or third eye rivalry in front of the mirror for you to experience it without any special device. And then the behavior patterns of the button press duration or contrast dependency on the dominance duration of the binocular rivalry. And then that this kind of behavior or phenomenological characteristic was used to back up the evidence for the monkeys to be also perceiving binocular rivalry. And then during that kind of situation, Rothesis and other colleagues have done an impressive series of work to do the neural recording, and then found that B1 to B2 are not really correlated with monkeys' percept, and B4 and MT were much more correlated, but some of them were anti-correlated with the behavior. And then when it gets to IT, then most of the neurons were correlated with the monkeys' report. Okay. So up until week 7, I put a couple of questions in the slides and also summaries, but haven't answered directly up until here. So some of these are, for example, in the case of the blind side, which we spent quite a bit of time, there was a subcortical pathway implicated as a sort of the culprit of this blind side behaviors. And subcortical pathway, especially superior colliculus and pulvinar, has been indicated as a very important substructure for attention. So that means something very interesting question, because blind side who lost conscious phenomenology still seems to have not only the behavior, residual behaviors, but has a potentially almost intact mechanism for attention. Then the natural question is, can attention work without consciousness? And that points to this question of relationship between consciousness and attention. And then the second thing is that when we talked about human single unit recording of binocular rivalry, these are always correlated with respect to the reports of the patient or monkeys. So if you think about this as a neural correlates of consciousness per se, that's not a problem, but it is also correlated with the reports. And consciousness and the report is not usually tightly correlated in everyday life. If you, for example, introspect yourself, you rarely report what you're experiencing moment by moment basis, right? So exact relationship between consciousness and the report is also another important topic to revisit this rivalry and also single unit recording. And then another question, which is the most important and also biggest difficulty is that how is it possible that different regions specialize to give rise to conscious experience or specific qualia. So for example, we talked about the V4, V8 for color, MT for motion, and IT for object, FFA for faces, and hippocampus for some kind of concepts. And this relates to this hard problem that was proposed by Chalmers. And so far, I don't think I have given any kind of possible hints to how to address this kind of question. Why, this kind of different neurons in different areas generates different percept. It's very unclear, because if you look at the data that I have been showing, then all you saw is this pulse of this firing, and it could be differently, modulated or different firing rate at the baseline or maximum firing rate for different areas. But it's really unclear why some particular neurons in hippocampus, which can maximally fire, let's say, 10 spikes per second, can generate concepts of Jennifer Aniston, while in neurons in V4 that can also fire, but half fire, let's say 100 spikes per second, can generate conscious experience of color. So these are the ones that are beginning to be addressed or thought to be addressed more theoretically in integrated information theory. And that's the kind of the things that we will be talking in the rest of the lecture from 8 to 12 in advanced topic, okay? And these three things are, in a sense, really at the frontiers of consciousness research. So this means that, it's a bit of the warning for the rest of the lectures. It contains quite a bit of my own research. And also I try to be balanced between, controversial part that I think, the answer is A, but, some people say, oh, it's not A, kind of controversy or debates. And I try to cover both sides, but I'm obviously aware that I'm biased towards my own opinion. And also this means that, many of the things that you will be learning from week 8 to this week to week 12 can be refuted or can turn out to be wrong in the wrong long time, perspective. It's also potentially true for week 1 to 7, but most of the knowledge about anatomical connections or neuronal biophysics are likely to stay true for next maybe 550 or 100 years. But many of the scientific discoveries are revised or refined across the time. So don't expect that all of these will stay true for the rest of your life. But the important thing is that week 8 to the rest could contain more sort of frontier, exciting kind of topics, but also it's more debatable or revised, possibly revised in a few years to 10 years, okay, shorter span. Okay, so having said that, in week 8, we are going to start examining the relationship between consciousness and attention. And learning objectives are to answer some of these questions, such as how can we define attention? What are the paradigms to manipulate attention? And what are the neural mechanisms of attention? And how can we explain the relationship between attention and consciousness? And for these matters, I refer to Quest for Consciousness Cox book, chapter 9 and 10. And then towards the end, I'll also talk about the global workspace theory that tries to explain the relationship between the attention and the consciousness. And that's an optional reading. Okay, so that's the plan for this week and the review up until now. All right, so let's start the first part. What do we mean by attention? So starting the definition of attention. And attention is obviously an everyday word. So many of you already have a grasp, and also, if you go to the dictionary, they give some definition. And intuitively speaking, it contains at least 3 components. One is a general arousal or alertness or readiness to do something. So this is a sort of a global activation level of the brain or behavior or sort of your level of arousal, conscious level. And this is, of course, valid measure or the concept of attention, but not really the target of the concept this week. And then also another types of usage of attention is, this is a bit misleading in many ways, but when you make an eye movement, then people talk about attention. Okay, so this attention, which is accompanied with eye movements, overt eye movements, meaning that explicit or direct eye movements, or continued with a gaze, is in a sense, attention in an ecological sense. However, when we try to dissect the relationship between consciousness and attention, it's just a confound. As I already explained, in many lectures, when you look at different locations, then the phobia has a completely different, representation, and you see differently at the phobia and the periphery. So when you are talking about attention to consciousness without discriminating, what you are talking is, actual eye movements, actual fixation, location difference, then many things could be already different. So this is one important thing. And the covert shift of attention, on the other hand, means that change of the attentional focus without moving your eyes. And I hope that you have been already doing this couple of lectures, but you can focus, and also you don't need to move attention, eye movements, from the fixation cross of this after effects, after image inducer, and then still attend to the periphery, or different kind of features or different objects of the vision. And this is the case of attention and consciousness research in many cases, because that one has much less confounding factors. Okay, and then after distinguishing these two things, the rest of the attentional concept is the focus of our topic. Okay, one is this selection, focus, concentration, and this is usually comes in two simultaneous operation. One is this enhancement or amplification of what you are attending to, and this comes at the same time suppression or inhibition of what you're not attending to. These two usually cannot be separated, and usually works in tandem, both in terms of neuroscience and also behaviors and also conscious experience. Okay, so this selection, focus, concentration part of the attention is the one that we want to capture in this lecture. And here's the most famous kind of definition of attention by William James, that's a father of psychology in USA. And this is highly widely cited. And maybe most of you have already seen this, and you don't have any problem with this definition, right? But if you say that that's totally reasonable, then that means that you're not attending in various ways. But say everyone knows what attention is. It is the taking position by the mind, it in clear and vivid form of one out of what seems several simultaneously possible objects or trains of thought. It implies attention is bullshit, attention is crap. Of course, the last two sentences is not what James was saying. And this kind of recognition or understanding of exact sentence requires both eye movements of this last sentence and also thinking or concentrating what this definition means. And here's the real definition. The last one is it implies withdrawal from some things in order to deal effectively with others. And this definition contains these three components of attention. Taking possession by the mind is corresponding to basically access or focus of what you are attending to. And then out of what seems several simultaneously possible objects or train of thoughts, this part is a selection, okay, or competition that we are going to talk about this week. And then withdrawal from some things, that corresponds to inhibition. It's always selecting or amplifying at the expense of something else. That's the attention. All right, and then attention, even if we define it that way, still there are lots of related concepts, and it's still confusing. So here's my attempt to make it more sense. Okay? One is this notion of a bottom-up attention. And roughly speaking, this is the attention component that is defined or induced or captured by the external stimuli. So for example, when there's a sound like this, then my attention is captured onto this one. Or if I see somebody coming into the room, then my attention is captured there. Even this can come with the eye movements, head movements, but also it doesn't need to be accompanied. So a covert shift of attention can be also captured. So this bottom-up attention or automatic or stimulus-driven task irrelevant. Task here means that when you're supposed to be doing some kind of task, let's say listening to the lecture or watching a lecture slide, something that is irrelevant for your current task is task irrelevant attention. And the exogenous means that in some stimulus that is in the environment and that is outside of the control of your own process. And then saliency based means that when things becomes conspicuous with respect to the surrounding, that captures the bottom-up attention. And sometimes this is equated as a pre-attentive process. But that's a bit complicated kind of a concept, so I'll talk about it later. Okay, then the other one, in contrast, is a top-down attention. And these concepts can be almost like opposite or dual to the bottom-up attention, and it is volitional. So while you are fixating here, you can volitionally control your attention to somewhere, and that's a top-down attention. And the goal-driven. So if you have some kind of goal to, let's say, move your hand over there or something like that, that's attention is already directed there, and that's a goal driven. And task relevant, so if you are doing some kind of task, that anything that is in the visual field that is relevant for your task is attentive in a sense. And the endogenous is the dual to this exogenous kind of component. You drive the attention by your own internal mechanism. And then in contrast, pre-attentive, it's sometimes called attentive, okay? And in addition to this top-down and bottom-up attention concepts, there are many different dimensions or distinctions of attention components. One is about the space. So if you are looking at, center of the display, you can covertly attend to, here or there. Spatial attention can be directed top-down or captured by bottom-up signal in space. And then same goes for time and the feature. Feature-based attention is, for example, if you are looking now at a display, and then when you're paying attention to these letters, then letter of blackness actually is a feature of this display. So attention is now directed to the blackness of your letter, and that's the sort of the feature-based attention. And I'll talk about it towards the end of this lecture as well. And then similar to the feature, but object-based attention is also operating throughout. So for example, if you are looking at this display, then anything in the display is generally attentionally enhanced, but everything else as a background is suppressed to some extent. And object-based attention can also work at the level of the word. So if you're attending to the word attention, then everything else is also slightly less attentive. And here's the summary table in the Christoph Koch's attention chapter in 9. And then here, bottom-up attention, for example, is characterized in, so the bottom-up attention is characterized to work in terms of space. It's throughout the field, whereas the top-down is spatially focused. And then feature-wise, it's across, it's working at all the times and all features and so on. And then it's related to the saliency, relating to the neighborhood features and so on. And then in the case of the top-down control, you can select specific feature. Like here, you can attend to the red thing here, and that automatically enhances the red thing over there and there and there, as well as this, part as well. And then duration-wise, bottom-up is usually captured only transiently, but the top-down attention you can sustain, by effort. Okay, and then the task dependency. So this is a sort of the task relevance and some positional control. So now, after covering this, definition of attention, we can start to talk about consciousness and attention relationship. Okay, and here is two types of the models that psychologists and philosophers have thought about or assumed for many years. So one, the model A says that attention determines what becomes conscious and what not, hence determines what we can report about. So here, this is the sort of the bulk of the inputs, sensory inputs across vision, audition, touch, and taste, blah blah blah. Okay, and then among them, some kind of attentional filters comes in, and then attended process gets enhanced and selected, and then becomes conscious. And then that is something that people report. And that's the one that behavior science of consciousness can deal with. And then on the other hand, B thinks that attention can first operate, and some of them are already unconscious. For example, like any kind of process that dies out at the level of the receptive field, or let's say retina up to V1 or something like that, then that may still not reach to anything further by virtue of being just weak or something like that. And then some of them are attended and some of them are unattended. And then again, unattended one becomes conscious, and then conscious report follows. So in both cases, the B is non-attention mechanism can operate for consciousness. Okay, and in both cases, attention and the consciousness is the same sort of, so it's redundant, but it's important. It's a serial kind of idea, and here you can actually be general to make it like this kind of model. First, there is some kind of filter for attention, and the attention is attended component is what we can report in the consciousness. Okay, so that's the one view of consciousness and attention. On the other hand, the other type of philosophical or psychological model, which is still serial process, is that consciousness comes first. So here, after the sensory input, some kind of typically philosophers thinks about this as a magical process. Magical process divides it into unconscious part and the conscious part of the feeling. So in the case of vision, what we feel like, this, conscious vision just comes in the first, and then some of the unconscious part remains completely inaccessible. And then within this, what we are conscious of, we can now direct attention for further sort of the processing. So let's say, now we are seeing this field, and then we want to attend more of this or more of that and so on. And that's the one that you can attend, and then eventually you can see it much better, and then you can report. Or putting it another way, when you're reporting something, it's automatically attended, and everything in conscious can be potentially attended, but conscious report is always preceded by attention. So that's another model. And then in other ones, it's many more inputs reach conscious states, yet to report about these, we need attention. That's another view. And from A to D, this is a serial models. And then here is one model that is a parallel process, but still thinks that the attention is necessary for consciousness. So here, the modeler thinks it's more to do with more prominently featured by the neuroscientists or cognitive neuroscience, this who knows that brain operates mainly parallelly. So here, input comes in, and then all of the processing is kind of processed in brain, and then attention can focus and also make some kind of spotlight of this processing. So this is a focus of the attention. And then that becomes available for consciousness, and then it can be reported. And everything else outside is unattended and unconscious. That's the attention is necessary view for A and C relationship. And then lastly, this is my, I'll just declare that, I think this is much more making sense based on the literature and also evidence, but consciousness and attention can be orthogonally operating. It's not to say that it's always orthogonal or, and so on, but first input comes, and then there are some kind of, conscious and unconscious kind of processing happens, and then attention can operate on some parts, and then here attended parts of the conscious processing and also unconscious processing can be both enhanced in terms of the processing, and then it can result in a conscious response or unconscious response. And then other parts here, these are, for example, it's not really available for consciousness and also unattended. The other part here, this is actually experienced and phenomenally sort of aware or experienced, and this is something that we will talk next week, but it's not really enhanced or selected, amplified by attention. And then this part is also consciously attended and also aware to the subject. And here, this part of the terminology, access awareness and the phenomenal awareness, is the one that we are going to talk next week. But just upshot is that this model thinks that consciousness and attention can work orthogonally and parallelly, and all these dissociation can happen. Conscious with or without attention, unconscious with or without attention. Okay, in summary for this part, attention in everyday language can be used in various ways, but scientifically precise definitions are available, and we need to talk about it in this way, okay, a more precise way. And it's important when you read or write things about attention, clarify what you mean by attention, because there are many definitions and sources. And more important for the neurobase to understand attention and the consciousness, it is important to distinguish this because the neuronal mechanism for attention could be different for different kinds of attention. And this could be also true for clinical investigation of attention and consciousness. And the corollary is that the relationship between consciousness and attention can be dependent on the kinds of attention. So, and towards the end, I also talked about various relationships between the consciousness and attention. And then in particular, distinction that is important, which we'll talk next week, is this: what we consciously experience per se versus what we can report about. So all these models, Victor Lamen, who was proposing this, model structure, always distinguish between what we consciously experience and what we can report about. And this is not that easy concept to understand, but distinguishing or not distinguishing makes a huge difference in terms of the interpretation or theory of consciousness and attention. So the next part of the video, I'm going to talk about how we can manipulate attention experimentally and then to interpret it. Okay, so now we are going to talk about psychophysical method to manipulate attention. To understand the relationship between the consciousness and attention, it would be nice to keep unrelated components unchanged. This unrelated component obviously includes this eye movements that we discussed, but also keeping the stimulus same is also ideal because we don't want to conflate the stimulus difference with the difference in attention or consciousness. So bottom-up attention, in that sense, is by definition stimulus-driven. So attentional manipulation also involves stimulus manipulation. So it's not super easy to understand what the attention and consciousness relationship is. So, but if you want to use the bottom-up attention type stimulus or paradigm, then what we can do is to manipulate these kind of factors and then study how attention consciousness relationship change as a function of the stimulus, or how the eye movements are consciously or unconsciously guided by the stimulus. And we are going to talk about this type of the studies next week. And then the first types of the stimulus that I'm going to talk is change blindness. So I guess some of you might have seen this change detection or change blindness paradigm, but I'll just show it nonetheless. You're about to see two images switching back and forth in rapid succession. And then your task is to spot the difference between them. Okay. Keep your gaze fixed on the center. And then if you can see the difference, then press the button or whatever. Okay. And then watch it again with the benefit of a covert shift of attention. Pay attention to the trousers worn by the man on the far left. As before, keep the gaze center. So this means that covert shift of attention is there. And then now you can probably see the difference goes to blue to brown. Okay. And then another one, keeping your eyes focused on the center. Don't move your eyes. And then can you see the difference? And then according to this, it says that none of the students in the class can find it. And then the car window on the right, you pay attention covertly, and then still look at the center of display, like here, okay, in the pointer. And then this is going to be again another discussion. And then here, just focus at the center. And then if you see attention, if you pay attention to the background behind the Jackson, $20, then you'll probably see it changing from black to white. Okay, so this is the change blindness demo. All right, then the next demo is inattentional blindness. So pay attention to this, 3 out of 6 peoples, and then especially the white team, and then count the number of the passes. Okay. Okay, so that's the demonstration of change blindness. And here is the demonstration of the attentional blink. So, but by attention blink, it means that your attention seems to momentarily blink, or as if I blink, and this is a demonstration. And throughout this demonstration, you basically try to find stimulus, Okay, stream of the letter will appear. It's very, very rapid, so you just need to focus there. And then try to find R, okay? If you find R, then you just press the button kind of thing. But right after R, if you see C, the letter C, then you're not attentionally blinking. But if you after trying to see R, if you cannot see C, then that's the erasing the next target, meaning the attentionally blink. Okay. So here it says that consciously noticing R or C in its own is not too difficult, but doing both is difficult. Okay. Here they come. Try to find R. Yep. Okay, I think you might have seen this again, but if the display speed is not right for the Zoom, then please go to this website again by yourself and then do the same thing. At least on YouTube, it should work. All right, then finally, there is this dual task paradigm for attention. Here, simply saying the attention is assumed to be a fixed resource kind of things, and then the benefit of attention is quantified by whether you can actually do two things at the same time. So it's a multitasking kind of situation. And the series of the experiment has shown that if you do something extremely difficult, like here, it's a 5 letters of rotated T's and L's. And then if you're asked to say that if all of the 5 letters are either T's or L's versus one of them is L's, like this one, versus 4 letters, 4 T's, or 1 T versus 4 L's, this turns out to be very, very difficult, especially if it's masked at the end by a rotated F. And this is known to be incompatible or difficult to do with a similar kind of attention demanding task at the same time. On the other hand, when you pair this central letter task together with some other stimulus, such as in this case, it's a natural scene, and then ask people to say whether that natural scene photograph contained either animals or not, then that can then test whether attention is necessary to do this task by comparing the performance of this natural scene task while you are doing this central task and natural scene task, or natural scene task alone. So it's a contrast between dual central and peripheral task versus single situation where you do only the peripheral task. And then if this and this performance is more or less the same, then that means that the exhausting attention by the central task does not affect on the peripheral task, meaning the peripheral task does not require attention. So that's the logic of this dual task. Okay, and then I'll just show you the demo for this dual task. And as this scheme shows that it's going to be very, very quick kind of task. The central task will be masked by stimulus onset asynchrony, and also peripheral task is also masked by peripheral SOA. And then both of them are matched to make the both of the tasks demanding when you do it on its own. Okay, so here is how it looks like. So first, let's do the central task only. Okay, so focus here, and then say whether all of the letters are similar, same letters or not. That's the same all T's. That's all L's. That's 1 L and 4 T. That's 1 T and 4 L's, and so on. So that's the central task. Okay, and then now, without moving your eyes from here, do the task again, but on the periphery, and then say it was an animal or not. Okay, and that was flower, that was natural scene, rocks, and that's a lion, and that's beetles, and so on. And then finally, under the dual task situation, you do the both here. Okay, so that's L and then lion. That's T and beetle. That's OT and flower. That's L and then rock. That's a kind of the dual task situation. Okay, let's go. And the point of this task is, in fact, you can do the natural syntax recognition with together with the central task without much impairment in performance. The next demonstration is this red-green disk situation. So again, central task is the same LT discrimination, but peripheral is now the discrimination of left or right side of the dot. The disk is green. Okay, so let's focus on the center and then say which one is red. So now I saw it on the left side is red. Okay, the next trial. Okay, again, left side was red. Don't move your eyes from center, okay? Right side was red. Okay. And right side was red, and so on. So here, if you try to do the central task together with peripheral task, now if you do it, if you try to do it, then what happens? Okay. T and 4 L's, but I wasn't sure. 4 L's and probably right side of L's. All T's and not sure. So this is a kind of the task that you can probably do both tasks at the same time. But again, we need to quantify and modulate the difficulty of the task individually. So this doesn't work. By the way, these are the response screen that actual subject is going to press on the screen in our experiment. So the left side is the same and the right side is this different for the letter task. And then here it's the red green and green red disk option is presented, and the confidence rating is clicked from 4 for sure and then 1 for not sure, and then 1 click can give a response for 1 task. Okay, that's a dual task. Next, the same dual task, but now the peripheral stimulus becomes now face discrimination, and your face discrimination task is going to be about the gender discrimination, male or female. And then this time, I'll try to do central task and the periphery at the same time. Okay, here we go. So the next one is the task, all else and the female. One L and the female. All L and the female. One T and male, probably. Something like this. So I probably made a mistake on the second trial, but roughly speaking, this face task is known to be possible even if you are paired with the difficult central task. That's the conclusion on the dual task. Okay. So the way to quantify this dual task is to first, quantify the central letter task performance to be, located here. And typically, this is a normalized version, but on average, people tend to use like 70% or 80% accuracy of the difficulty. And then the peripheral performance is also set to be 80% accuracy, very difficult. And then when you do the central only or peripheral only, it's 70 or 80%. But if you do both at the same time, for example, this dot corresponds to that the task is peripheral task is around 90% of the 70%. So that means 63% of the peripheral performance together with 90% of the peripheral. So that's a 72% accuracy, and so on. And then if you do it, multiple times, it locates to this top corner, more or less, meaning that there is a little bit of, if anything, the degradation of performance here. And then here is that task is animal versus non-animal. And if you do the same thing with the animal versus distractor, including the city scene or vehicle, the conclusion is the same. You can do it, without much cost. And then if you suspect that the animal is really the special kind of the thing, and then you can do the experiment again using the same set of the stimulus as B, but now change the target to be vehicle. But again, you don't see much difference in terms of the performance. On the other hand, if you do this dual task with green-red disk like this versus this, then almost always performance is located along this diagonal. What it means is that if you try to prioritize the central letter task, then your task performance for the peripheral green-red becomes chance performance. On the other hand, if you try to keep your performance of the periphery at the normal performance, then your letter task at the center becomes chance. And then if you try to do both, then your task is always almost like a trade-off between them. So the height, or sort of this distance between this diagonal line to the average performance here is a measure of the attentional requirements for the peripheral task. This requires attention. That's the reason why your performance aligns here. And natural scene stimulus or male-female discrimination tend to locate here, meaning that it doesn't require attention. So in summary, I just briefly described a couple of attentional manipulation paradigms. And then there are many paradigms available to manipulate various aspects of attention. And the various aspects are the ones that I reviewed in the first part of this video. And then to study the relationship between attention and the consciousness, keeping the stimulus or consciousness or behavior is always ideal. And in that sense, manipulation of the bottom-up attention is always difficult to interpret. So you need to be careful. But promising manipulation of the top-down attention includes, so here you don't change the stimulus input, okay? But you just change the covert shift of attention, like let's say in the case of the dual task, you always look at the center, but you change the attentional location. And the change blindness was also like that. Inattentional blindness was also like that. And then just change attention through the instruction or expectation. And the change direction and change blindness and attention, inattentional blindness are also involved in this expectation. Okay. On the other hand, so this means that the key paradigm in the future are likely to be the change or inattentional blindness and how it actually interacts with other factors of the consciousness or visibility. So this is mostly the spatial attention or expectation component or crowding that we will be talking next week. And then attention blink and the backward masking is kind of related, and it's a relationship between the attention and the consciousness in the temporal domain. And then the dual task. And how much, so now we have actually learned these types of the manipulation of attention and how it can potentially affect on the consciousness. We need to go into a little bit deeper on how much do we know about the neural mechanism of attention, and with what we know so far, I mean, in science of attention, how much we can actually explain these types of the attention and the consciousness phenomenology, and that's the next part of the video. Okay, so what is the neural base of attention? The key features to consider visual attention is the distinction between top-down and bottom-up, spatial, temporal, feature, object-based attention, which type of attention we are talking about, and then the hierarchical organization of the visual cortex. Okay, and there are many types of the attention that is not visual as well, auditory and also arousal, but most of the what we know about attention is coming from the visual science. So these are quite important kind of consideration. And then another key features to consider is competing neuronal interactions operating for underlying the attention. And neuronal interaction wise, I talked a little bit about the neuronal model of the visual binocular library last week. And this is also highly relevant for attention. So first, just to go back to a couple of weeks ago of knowledge, I emphasized that there is this architectural kind of feature of the visual system where the receptive field size expands as you go from lower visual area to higher area. So for example, if the center of the receptive field is here, the B1 receptive field is small, and then B2 tends to be bigger. But again, this is a bit confounded by the fact that the eccentricity also goes up. So when you are fixating here, and then if the same eccentricity size is kept, probably B1 neurons tend to be like this size at this location, and B2, and then B4, and then IT. Kind of that's a sort of the structure of the receptive field. So this particular figure from Christoph Koch's work is a bit exaggerated because it confounds both eccentricity and the size effect of the receptive field. But nonetheless, generally speaking, at the given location, receptive field becomes bigger as you go across the hierarchy. Okay, and then the key concept here is that what you are, if you are imagining that you are the neurons in, let's say, IT, okay, and then if you are receiving the input from the B4, then the B4 neurons might say that, oh, there is a face here, or face here, or not face here, and not face here. And the IT has to make a sort of the computation, and then eventually it seems to be doing the face detection as a function. And that could be regardless of where the face is within this IT's receptive field. And to achieve that kind of function, what it needs to do is to consider or sort of weight the evidence from lower visual areas to trust or make a decision of what kind of information to pass on to downstream neurons. Okay, and I'm going to give a very simplistic neuronal model of how it can be achieved. It can achieve such a computation in the next slides. So first, let's consider retinal stimulus. Presentation of the stimulus looks like this rectangle, and then let's suppose that subjects are fixating at this location. So it's projected on the left visual field, and then this is a rectangle. And then, as you might have already learned, all these left hemifield stimulus is going to be presented or processed on the right hemifield of the B2. Okay, and then there is some kind of cortical magnification and so on, but I'll leave it for now. And then suppose you find neurons that responds to all these four edges corresponding to this one. It's flipped, but I'll just to simplify, I'm not going to talk about the flipping of the side and also up and down. And then you also find neurons in V4, and that appears to be connected from B2 in a way that this neuron that detects this line at this location to be projecting into this V4 neurons and so on. And then as a whole, this V4 neuron detects a shape like this, rectangle or square in this particular location. And you can find something like this in V4 IT, but this is a sort of model neuron, okay? And then for our purpose, what's important is what happens in terms of neuronal response. And then over the time here, let's suppose that I don't present this stimulus, square stimulus initially, and then at time 0, I present it for, let's say, up to until 1 second. Okay, and then after that it's off. And then simplifying all these response, I simplify that all these neurons immediately respond and then do not decay and so on. Then I show the firing rate of each of the neurons here. So this goes from 0 to, let's say, 50 hertz, and then this also goes to 0 to 50 and so on for each of the neurons. And then this model B4 neuron would be also excited by each of these inputs, and then it fires like crazy, but it saturates its firing rate at some point. So let's say it goes from 0 to 50 hertz or something like that. Okay, that's how this neuron would respond when there is no attentional situation and just presenting as stimulus that B4 likes. Now, consider the next situation where I present only the stimulus in one of the edge for this square, and then nothing, or very weak stimulus for the rest. And then this particular neuron that prefers this location and this orientation still continues to fire from 50 hertz. Okay, but the input into these V4 neurons are much weaker to other 30 location. And this guy is the only one that produces very strong 50 hertz inputs. And as a result, it produces slightly less firing rate, okay, compared to when it produces very striking a strong input with 4 squares and so on. And remember that I said that these squares are much just weaker and not really absent. So it's still, we can see it as a sort of square in this case. All right, then next situation. So suppose that I present one of the location as a non-compatible or non-preferred stimulus for this particular neuron. And it could be colored in red, but this is just for the visualization purpose. So instead of this nice triangle, now I present this unclear kind of stimulus. And in particular, this stimulus is going to suppress the V2 neurons here, okay? So here, the neurons are going to respond, usually at 50 hertz, but it becomes much weaker in terms of firing rate. So it goes like, this baseline, almost like baseline firing rate. It's kind of difficult to draw, but you know what I mean. So it gets, lower firing rate for this particular neuron. And then that generates, and the other neurons are, also weakly exciting this, B4 neurons and so on. And this neuron actually, now that, it's much weaker than the, usual firing rate, it actually provides the inhibitory inputs to this neuron. And as a result, although, some of these nicely kind of looking faint square-like stimulus generates a little bit of the firing, it generates overall much weaker firing rate. So non-preferred stimulus inhibits V2 neuron, and V2 neurons inhibit further the V4 neurons when it's incompatible with the overall shape of the preference. Okay. So that up to here, it's nothing to do with attention. It's just a purely the sort of simultaneous recording type experiment between B2 and B4 with a different stimulus preference. And then the important consideration comes when those preferred stimulus in the top right and non-preferred stimulus in the bottom left is simultaneously presented. So in this situation, B2 neuron top right is going to fire a lot, and then the top left and bottom left is going to be inhibited or suppressing other neurons. And what happens in terms of B4 neurons? Assuming that monkeys are doing, or humans for that matter, are doing something neutral to these two stimulus, what's happening is usually something like this. So B2 neurons are firing like preferred or non-preferred stimulus, as I explained before. And then B4 neurons tend to fire intermediate between the suppressed situation by non-preferred stimulus alone or preferred stimulus alone. And it's intermediate. So it's not super complex, okay? And then what attention does is to bias this firing of the B4 neuron in one way or the other. So for example, if some kind of attentional mechanism kicks in and then select and amplify a little bit of this guy, and then if there is an interactive sort of interaction between this neuron to this neuron, then there can be some kind of inhibitory inputs here. And then that also, cuts all these, inhibitory activity from B2 to B4 is now suppressed. And as a result, what you tend to see is that the B2 doesn't change much, in terms of observed firing rate, because, but at the B4, you see, recovery of the attentional effect, of the response due to attentional effects in this case. So that's this kind of, response. Recovery through the attentional amplification. And, within B2, it can be the case that, this attention can change a little bit of the firing, but it doesn't have to be very strong as long as this, B2 to B4 activation coming from many neurons in line with this idea. And that tends to be what we observe in the neurophysiology experiment. On the other hand, if you attend or some kind of attentional biasing signal amplifies this neuron's firing, and then this neuron is interacting with this neuron and then suppress the firing, what happens? So now B2 neurons, which this may be a bit confusing, but that neurons that prefer this orientation becomes active and enhanced by the attention, and that guy can suppress this neuron. And then as a result, the strong inhibition is still there, and then the excitation from this nice neuron is not there anymore. So now, as a result, overall, B4 neuron response tends to become closer to when stimulus was presented here alone. I hope this is clear. Okay. And then John Reynolds has done exactly this kind of experiment in monkey B4. And what they found is summarized in this figure. So as I said, the baseline condition here, that is both stimulus presented is intermediate compared to the good stimulus, preferred stimulus alone, or poor stimulus alone here, right? For the particular neuron. On the other hand, this when the preferred stimulus is attended, then this, both stimulus situation, the stimulus itself is the same here and then here. But now response of the neurons are almost the same as when the good stimulus was presented alone. Okay. On the other hand, when the poor stimulus was attended by the monkey by some task instruction or task relevance, then although the stimulus itself is the same, but the response of the B4 neurons almost looks like first stimulus alone. So this kind of idea is compatible with the fact that, when you attend to some stimulus, then that's, consistent, that's, what we become aware of. Okay, so this is the type of neurons in B4 that goes with attention and perception. And I mentioned in the beginning that there is a class of attention now, which is called feature-based attention. And in the case of the feature-based attention, the task tends to be something like manipulated by the instruction. For example, here the task instruction is indicated by the color of the fixation cross, either white or black. And then your task is to report the orientation of the color that matches with this, central fixation. So here, after stimulus presentation, you need to remember all the, stimulus and then attend to all of them. But then at the discrimination phase, you need to report, oh, it was, so this is a, left hand. In this case of the trial, you need to report the orientation of the white stimulus. So you are going to press the button for left tilted or something like that. On the other hand, this black one trial, you need to report in the end black orientation. So it's right in this case. And so the key here is that the instruction is different between the match and non-match condition. On the other hand, during this stimulus presentation period, that's the most critical recording period for this experiment. Everything except for this central fixation point is the same. And then the researcher can record the neurons that have a receptive field around here, right? And then you can make the stimulus either preferred or non-preferred for this particular V4 neuron. Okay, and then when you do the recording in this situation, what they found was something like this. So when the monkeys the neurons preferred stimulus was presented, here this is a preferred stimulus, okay? And then the task instruction is matching with the feature of this, preferred stimulus. Then the firing rate is very high and then sustained. However, when the unpreferred stimulus is attended here, okay? So it's a non-matching situation. Your preference of the neuron does not match with what the monkey is trying to do, which is to remember black, pattern. So monkeys are presumably attending to all these, black thing. Then this white orientation, which actually neuron prefers, gets suppressed. And this is sort of the similar kind of mechanism, through the similar kind of mechanism that I explained before about spatial attention that John Reynolds reported. Okay, it's a bit different kind of mechanism, but idea is similar. Okay, so just to summarize the neural basis of attention so far, the core principles of the bias competition model of attention is that first, attentional effect gets stronger when the stimulus itself induces a lot of competition. Okay, unless there is a stimulus, then you can't operate on this inhibitory mechanism between the neurons. And for the neuron to operate on the attention or benefit from attention, neuron has to receive many inputs from many different kind of neurons, and that kind of situation is expected to occur with the higher visual areas, which has the neurons that has a larger receptive field, like IT or FFA or PPA or V4 compared to V1, V2. These guys are likely to be benefiting from attention because there is a potential competitive candidates. And psychologically, all of this can translate that when some biasing process operates. So this part I haven't actually explained, but instruction, expectation, or memory template matching kind of stuff happens, then this biasing signal can operate and result in attentional modification. And if all of the things work together, then as a result, conscious perception can drastically change without change is in the stimulus, which is what we wanted to achieve. Okay. So what is the source of the biasing signal, which I haven't actually discussed yet? And one of the most likely candidates is this frontal or parietal area. And when they are impaired, some of the patients exhibit neglect or extinction. And that's what we're going to see with the video.
Because Alan's middle often isn't it?
The middle is the right.
You must always eat on the right side, but not on the left side. Just leave that.
Give her a dinner plate and she'd only eat the vegetables and leave the meat, which is disappointing because I was a cook.
So if you start to picture, it can not fit in the paper if he gets over to the left because he hasn't left enough room.
Spatial neglect is a syndrome, that is signs and symptoms that patients most frequently have after stroke, but sometimes in forms of Alzheimer's disease, where they ignore one side of space. So people, objects and sounds on one side tend to get ignored, and the patients who have it tend to be drawn to the other side. And this can extend to things like the food on the plate in front of them, that only eat food on this side and then say they're finished. It may extend to parts of their own body. So when trying to shave, they may only shave this side of the face and miss out this side, put makeup on.
So you can only see from across there?
Yeah, from there to there. That's my vision.
So what's going on in the other half?
Nothing.
There's nothing at all.
Because often I've come up from this side to give you something.
Anybody can creep up my left, I
And
wouldn't
he
know they were
doesn't
there.
see anything.
I can't sense them.
So if you just look at me and just point at the finger that moves, okay? Or say both of them. Tell me which finger moves.
First one.
Okay.
That one.
There.
No.
Look at me.
That one.
Okay. Look at me.
That one. That one. That one. That one. That one.
They tend not to describe the condition, to be honest. One of the most intriguing things about it is that this sort of loss of attention for one side of space doesn't leave a great gaping hole. And that's why it's very useful to contrast it when someone's got what's called a hemianopia, which is a primary sensory deficit. They can't see that side of things, and they know they can't see it. So they're constantly moving their heads like that. Whereas patients with neglect are unaware of their deficit, that they're not even aware that they're missing something because their sort of imagination of space has gone on that side too.
Does he have a name?
I don't know, I haven't thought of one.
I can stand right next to you, can't I? You can't sense
No,
one there.
no, you can't. If you told her to look, she'd actually look around that way, like that, right round on the right-hand side, and then come back to central. She wouldn't actually think about coming and looking around to the left as well.
People often say, why don't you just tell them to look to the left? And relatives can be very frustrated about this too. And I think you've got to be aware that the process of attention and these higher visual areas are involved in the representation of space rather than just seeing things where they are. See the lines there?
Split them in the middle.
Yeah, that's one end, that's the other end. Show me where the middle is. Mark the middle for me.
I was only looking at a line from there to there. It's in the middle of my line, not the middle of your line.
So the first time I saw you, that's where you were marking the centre of the line as well. Patients realise something's wrong when things are pointed out to them over and over and over again. So in a way, I think for them it's slightly abstract, that they know that there's some problem on the left-hand side and they're not aware of that problem, but they know everybody's telling them they have to do something more on the left. And so they use strategies, things like that, to try and overcome the problem without really being to appreciate it and being able to appreciate it in its fullness.
I remember getting those word search books, and I remember it was only one side was always ever filled in. Yeah, and then slowly she got better and better at it, because I used to say to her, Colby, you know, I'm not getting value for money, you're only doing half the time. Yeah, so slowly she learned that, yeah, start learning, you know, do the left side first, and then come back to the right.
Some people have it soon after their stroke and it gets better within a few weeks. And then another group of people have it long term and learn strategies to overcome it. So if you probe deeply, they still have problems with attention. Even that bias may go away, but they still have deep problems when trying to find things. And then they also tend not to remember where things are after they've looked at them. They have poor working memory for space as well. So a lot of these deficits don't recover, although people can use strategies to overcome them.
Give that a please if they find you. That's good.
Okay, so the video basically showed the patients who have an likely lesion in the frontal or parietal areas, and as a result, it tends to generate a neglect or extinction, as explained by the patient's report. And these tend to happen from the right side of the parietal cortex. That's a sort of classic story about the neglect or extinction. And neuronally, what's more clearly found these days over the last 20 years is that the involvement of the frontal areas in monkeys. So here, FEF is the area for called frontal eye field. It is very important to control for the eye movements, and without this, monkey cannot make an eye movements. Frontal eye field. And this side is eyes, and then this is a B1. Okay, so it's located in quite far, front. And then what they this Moore's Turing Moore's experiment did was first to locate the receptive field of the B4 neurons. Okay, as I said, B4 is. So what this Turing Moore's paper did first is locate and characterize the neurons in B4's preferred stimulus, and also the receptive field location and extent. So here, monkey is fixating at here at the center, and the bottom left is the location of the B4, which is located to the right side of the B4 in the top, dorsal areas. Okay, and then when the stimulus was presented like here, this is over time. And then when the stimulus comes on, B4 neurons start to fire really like crazy when it's preferred stimulus. Okay. And then on the other hand, FEF, frontal eye field, they put electrodes for the micro stimulation. And FEF is known to generate eye movements, especially when it's produced, when the stimulation magnitude is strong. So patients stimulated in FFA, if you do it with a human, then, and also if the extent is really micro, then most likely columnar organization of the FEF allows the neurons within the FFA, which has a similar preferred, movement field, or the target of the motion of the eye movement, to get activated together, and then that induces eye movement. So here, one particular area of the FEF stimulation resulted in the movement of the eyes toward the bottom left here. So eye position goes from nothing to something here. And then this is the duration of the FEF stimulation. Okay, so the setup is that B4 is recorded, and then FEF is also stimulated, and then they match the location of the B4 receptive field and FEF movement field or eye movement field. This is a very demanding kind of experiment, and that's why in 2003 it went to Nature, the top journal. And then what they found is the following. So if the receptive field and the movement field matches, then when the stimulus is presented from here, time 0, and then 500 milliseconds, then B4 neuron starts to fire a lot and then decline like this. And then around this time, black is the one without stimulation. But around 500 milliseconds, if they start to stimulate FEF a little bit, so that it doesn't induce eye movements, then that's the reason why they present this horizontal and also vertical eye movement trace. So this stimulation doesn't cause eye movement at all here, right? And then what happened was that the V4 neurons firing rate systematically enhanced. The red is the part that is a recording average of V4 neurons. So what it means is that when there is a subthreshold activity in FEF that doesn't induce eye movements, it still increases the firing rate of the V4. And that corresponds to our sort of the covert shift of attention. Covert shift of attention, according to this type of the experiment, can be explained by sort of a subthreshold eye movement, which shifts attention only, and then response at the attended location becomes enhanced, almost like when you are preparing the movement to that area. That's the sort of the finding here. And the important thing for us is that this kind of biasing type of idea that I introduced in the simple model can be coming from a frontal area, in this case FEF. So with this much of what I told you about attention, neural basis of attention, source of attention in the frontal apparatus area, and also a competition from B to B4 interaction, can we actually explain attention-related blindness? To some extent, we should be able to. For example, in attentional or change blindness situation, as you remember from the demonstration, typically these stimulus contain lots of complicated stimulus. Like in the case of the initial change blindness, you saw that there is a natural scene, and the natural scene itself contained lots of people and objects like cars, grass, and things like that. And then in the case of the change blindness, you don't know what to attend. So many of the things are sort of competing each other, and then especially periphery, it becomes kind of suppressed or enhanced depending on the chance. And to notice a difference, you need to sustain change and also after change, before and after change kind of stimulus. And usually your attention actually shifts much faster compared to this change. So over the time, you don't remember the change, even momentarily. And that's one way to explain change blindness. And in attentional blindness of the gorilla thing, remember that that video first asks you to pay attention to the white t-shirt team. And that means that the feature-based attention to the white becomes very strong. And on the other hand, to make this feature-based attentional enhancement for the white, you also simultaneously have to suppress the black team's t-shirt, right? Because it is competing, in fact. And because this black thing is in general really suppressed, and that's probably the reason why gorilla is not experienced really strongly, because it is actually suppressing, actively. And attention blink and masking is also similarly explained in terms of the temporal version of this competition idea, probably. And the important thing is that all of this is potentially explained by the failure of the signal amplification and also too much of the suppression. And that leads to this idea of global workspace theory of consciousness. So here is a very complicated 2x2 design matrix or sort of the table. And let me go through first the row. The row is the strength of the bottom-up stimulus. And you can think of this as a sort of stimulus contrast or duration and so on during the masking. And it can be either weak or strong. And then top-down attention component here can be either absent or present. And then when it's absent, this model suggests that things that is coming from frontal apparatus doesn't reach the visual cortex. So the weak or interrupted things just doesn't get activation or amplification, and then no reportability result. And basically, it's a subliminal, non-conscious, unattended. And then if the stimulus is sufficiently strong, then what they call is a pre-conscious stage. So it is an intense activation of the occipital area, like V1 to V4, potentially FFA and also IT, but it's confined to sensory motor processes. And then occipital or temporal cortex generates some kind of loopy activity and the local synchrony. And then it still doesn't result in reportability because attention is now occupied somewhere. Here, this is a somewhere symbol. And they don't call it as conscious. On the other hand, then when the stimulus is weak but still amplified by attention, this model says that attention can reach to enhance a bit of this occipital. And then it enhances the feed-forward activation up to, let's say, FFA and so on. But it doesn't lead to a very sufficient kind of strength of the activation because stimulus is weak from the beginning. And as a result, it doesn't lead into the front parietal activity. And we can't also see it, and then we can't report it as a consciously seen stimulus. What distinguishes, according to this global workspace theory, is this conscious state requiring both top-down attentional amplification and sufficiently strong stimulus. And that is, in a sense, marriage of the prefrontal and parietal amplification signal and the bottom-up signal strength itself. And this corresponds to intense activation of the parietal frontal network and long-distance synchrony and the conscious reportability. Okay, this is the global workspace theory. And at this point, I should say that I'm not very convinced by this model, but that's going to be coming to the from the next week. Okay, but this is a highly popular model in the consciousness research right now. So, in summary, in this section, I explained the neural basis of attention. And it's primarily coming from the biasing signal from the frontal or parietal cortex, and that tries to resolve the competition. And for this to work, you need an overlapping receptive field in a very large kind. So that's likely to be located in higher visual areas and bigger overlap between the receptive field. And then one of the most promising model to explain this attention and consciousness relationship is this global neuronal workspace theory, GNW. And this can explain various aspects of attention-related reports of blindness through the failure of amplification of the top-down, by the top-down attention and reaching to the global workspace. So global workspace basically explains something is reportable when it reaches, when something is strong enough and amplified enough so that it reaches to frontal and parietal area. And this tries to primarily explain the conscious reports. But at the time of the proposal, people didn't really distinguish between conscious experience per se versus conscious reports, or at least we didn't have a tool to dissociate these two. And so that became quite, popular. And as I argue in the next weeks, now we can have a couple of, interesting situations that can tell the difference between experience per se versus conscious reports. And one of the biggest kind of problem of the global neural workspace is that the link between the neural activity and the consciousness remains really unclear. So it is explained that something that enters into the frontal or parietal areas becomes conscious. But what I reviewed until last week is that these sensory areas such as V4, IT, or FFA, all these local areas of the network generates conscious experience of the color or motion or face and objects. And input to the parietal or frontal area may be slightly different for each of the different kind of qualia, but how this differential input pattern, if there is anything, can distinguish what we experience is unclear. So they need to probably propose or think about the way that prefrontal or parietal areas kind of decodes or transforms the input pattern into conscious experience, but that part is never explained, because primarily global neural workspace is a theory about how it's possible that we can report something, but not in other situations. So the next week, we are going to address several of the questions. So this is a bit of the preview. Is attention necessary when there is no competition? So I talked about many of the neural bases of the attention as a sort of that coming from the competition. So if there is no competition to begin with, is there any role for the top-down attention? That's one question. And then can this biased competition model explain the findings of the dual task? That's another question. I briefly mentioned, and if you see the demo and then try to do it by yourself, it has been shown that natural seeing, animal presence or absence, or vehicle presence or absence, or face gender, these kind of things are possible to do under the dual task. However, the disc orientation discrimination, red-green versus green-red, that's not possible under the dual task situation. In both cases, it seems like there are lots of competition going on, but only the case of the green-red seems to be a case where we can't see we need an attentional amplification. So there seems to be something more than the biased competition that attention is doing. And what's that is still unclear. Potentially it's a binding, but it's a sort of a frontier of consciousness. And then lastly, if you think about the biased competition model or global workspace theory, then attention should be able to operate on both visible and invisible stimulus. And this is a kind of the dissociation that drove the last 20 years of the attention consciousness research. And we are going to talk about it next week. See you later.